Right, well, welcome. Thanks for joining. What we're going to cover today is high-speed 1760. We're going to cover an overview. I expect this to take about a half hour. I reserved an hour in the invite, but my intent is not to take an entire hour for this. So let's try to keep it short and sweet and interesting and not overly long. All right, what we'll be covering today in the tutorial, the overview, is we'll be talking about high-speed 1760, the high-speed 1760 bus, and how it relates to, by providing an overview of the related protocols. So we'll talk about Fibre Channel, we'll talk about FCAE 1553 or Mil Standard 1553 over Fibre Channel. We'll talk about the weapons bus, or the weapons interface, the aircraft to weapons interface, Mil Standard 1760, and then HS1760 B, which is better known as HS1760. So that's the definition of the high-speed 1760 bus. Also, just for everybody's information, this is the first of a multi-part webinar series that we'll be providing at AIT. So there will be follow-on webinars coming every few weeks to a month after this, diving into more depth on some of the parts we cover as an overview today. So think of today as an overview, and then look out for more invites for future webinars that are going to dive deeper into some of the topics that we just introduced today. So first, we're going to talk about Fibre Channel today. Fibre Channel, it's the base protocol for high-speed 1760. So 1760 is built on top of Fibre Channel. So to understand high-speed 1760, you have to understand some of the basics of Fibre Channel. Fibre Channel is a high-performance network, and it's been deployed even prior to high-speed 1760 on several aircraft programs and platforms. Those include F-16, also on F-18, F-35, on the B-2, and also on E-2D, just to name a few. This certainly isn't an exhaustive list, but it's kind of a highlight bullet. Fibre Channel supports three possible network topologies. So point-to-point is the first one, a very simple topology where you have two end nodes or two devices that communicate with each other over a direct connection between the two devices. So Fibre Channel supports that kind of topology. It also supports an arbitrated loop topology. So in this case, all of the devices that are communicating on the network are connected in a ring network or a loop. And then what's probably the most common that everybody's familiar with is the switched fabric or a switched network, where you have end nodes connected to switches or a network of switches that route data traffic between the end nodes through the switching network. High-speed 1760 uses the switched fabric network topology only. It doesn't call out or make utilization of point-to-point or arbitrated loop topologies. So you won't hear much more even in this series of webinars about the arbitrated loop or the point-to-point topologies and specifics of Fibre Channel related to those topologies. We're going to concentrate primarily on the switch fabric, since that's what the weapons bus uses. Some basic Fibre Channel terms. So a node, think of a node as an end system or a device on the network. So if you're talking about avionics, think of it as an LRU or an avionics computer. A node can have one or more interfaces to the Fibre Channel bus or Fibre Channel network. Those interfaces are called ports. An end port specifically is the type of port that's at a node on a Fibre Channel device. And each port has a bidirectional connection to another port at the other end of a link. So a link is bidirectional in Fibre Channel. So typically, if it's an optical physical network interface, it's a strand of fiber optics that is transmitted in one direction, and then another strand with the data coming in the other direction on the link. Fibre Channel isn't limited to fiber optic. It can also use copper, a copper interface or an electrical interface. So in that case, also you have a electrical interface going in both directions to create a bidirectional link. Over on the right is an example of a switched network, a switched fabric network. So you have a set of nodes. Each node uses an N port to connect to an F port in the fabric or the switch. So an F port is a port in a switching element in the in the switched fabric. And then another type of port is an E port. Those are the type of ports that connect between two switching elements in the backbone of the network. So N port at the end nodes, F port in the switches, and then E ports for inter-switch connections are some of the basic terminology. Fibre channel, the Fibre Channel protocol is layered in I guess in compliance with the OSI model of layered network protocols. The lower half of the layer, so FC0 up to FC2, are think of those as happening and being in the context of a port at a node, so one of the ports, and then from FC3 and up, those layers of the protocol are more, the context of them is the whole node or the whole end device. So those upper layer protocols may specify, use or how to use and utilization of more than one port within a node. When we talk about the data hierarchy within Fibre Channel, and here we're specifically looking at the FC2 layer where exchanges, sequences, and frames, flow control, all the basic communication rules that go on a link between two ports. We're going to talk a lot about the data hierarchy. So at the bottom level of that, you have a frame. So a frame is, think of it like an Ethernet frame. It's an individual unit of information on a link. Multiple frames can be combined together and contained within a concept called a sequence. And then the next layer up, multiple sequences can be combined and contained within an exchange or a protocol exchange. So exchange can contain multiple sequences. A sequence can contain one or more frames in Fibre Channel. We'll look at the frame format first. So first, at the very beginning and at the end of the frame, you see idle frames. So on a Fibre Channel link, there's always something being transmitted from the transmitting side. So when actual data frames or link control frames aren't being sent between the nodes on a port interface, the link is filled with idle frames. So there's always something being transmitted to keep the transmitter and the receiver in timing sync on a Fibre Channel interface. Then when an actual frame is going to be transmitted, there's a 4-byte start of frame sequence that comes out to signal that an actual frame is coming. That's followed by a 24-byte frame header. And then after the frame header, if it's an actual data frame, you would have a data field that can be up to 212 bytes long, and then that data field would be followed by a CRC, a cyclic redundancy check over that frame. If it's a link control, there's no data. All of the information to be conveyed on the link is held in the frame header. The 24-byte frame header consists of several fields there. So just quickly run through those. Don't intend to get into too much detail about this today. That would be, the details of this would be coming in the follow-on webinars where we dive into more detail. But at the front of the frame header, you have the routing control field. At a high level, this is going to indicate what kind of frame it is. Is it a link control frame or is it a data frame, as an example? Then the CS control, or the class of service control, that's really going to specify the priority of the frame. So Fibre Channel has mechanisms built in where different data flows can be prioritized. So you can do things like carry connectionless data or signaling data on the same network as you would cover something that's maybe more time critical, like a video stream. And so the CS control field would be used in cases like that to indicate the priority of the frame and indicate that to switches and intermediary nodes between the source of the data and the receivers of the data. Then you have the source and destination IDs. So these are the addresses of the ports, the source port and the destination Fibre Channel port that the frame is intended to be sent to. Jumping down, I think probably the most interesting next pieces are, we talk about the frame being the basic element, and then frames are contained within sequences. So you have the sequence ID and the sequence count. Those are used to manage sequences. We'll look at those, the use of those in the next slide. And then multiple sequences can be combined into exchanges, and you have an originating exchange ID and a receiving exchange ID that you use to identify which exchange a particular sequence is associated with. Pardon me. As I said, a sequence is a series of one or more fiber channel frames. And then an exchange is a series of one or more related sequences. So here you can see you have an initial sequence. So the originating end port gives that sequence a sequence ID of 1 and then a sequence count of 0. So it's only a one frame sequence. Then you have another sequence that's presumably being sent in response to the first sequence coming from the other end of the link. That would have a different sequence ID assigned by the originator, and since it's only a one frame sequence, the frame would indicate a sequence counter of 0. Then as a response to that, you could have another sequence, and in this case, the sequence consists of 2 frames, so both frames have the same sequence ID, but we can see which frame is first and which frame is second in that sequence based on the sequence count field in the frame header. And then you have a single sequence, a single frame sequence coming back as a response to that previous sequence. So combine all these sequences together into what's called an exchange. So presumably the end port on the left would use the same originating sequence, or originating exchange ID and all of its sequence frames of the sequences in that exchange, and then same thing for the destination exchange ID coming from the other side. Exchanges can occur between 2 ports, and they can be either in one direction or both directions. So, I'm sorry, they can include sequences that go in one direction or both directions. So in the previous slide, we showed an exchange that had sequences going in both directions, but it's perfectly legal and supported to have an exchange that includes multiple sequences that only go from one source port to the other destination port. Doesn't have to be bidirectional. An example, we're headed towards talking about 1553 over Fibre Channel, or FCAE 1553 here. Pardon me. An example is in FCAE 1553, an exchange would be used to do the analogous of a network controller to network terminal, or a BC to RT transfer. So you would have the initial receive command set within a sequence to the network terminal. Then if there was any data that was part of that, you would optionally have sequences of data. And then the network terminal would acknowledge receipt with a sequence going back in the other direction to the network controller or the bus controller node. That would be a sequence of frames indicating the status back to the controller. Okay, we'll start talking a little bit about FCAE 1553 or Mil Standard 1553 over Fibre Channel next. So we've kind of laid the groundwork for the base protocol, which is Fibre Channel. HS1760 utilizes 1553 over Fibre Channel, so we'll talk about FCAE 1553 next. FCAE 1553 is an upper layer protocol, so it lives in the protocol stack up here. And what it does is it defines a set of Fibre Channel sequences and exchanges that are used to execute 1553-like communications. So NC to NT exchanges, which are analogous to a 1553 bus controller to remote terminal transfer. NT to NC exchanges, analogous to a 1553 remote terminal to bus controller transfer. And then NT to NT exchanges, which are analogous to RT transfers in the 1553 world. A little bit of a comparison between 1553 and 1553 over Fibre Channel. With your standard 1553 bus, you have a 1 megabit per second max data rate, up to a gigabit per second with FCAE 1553. The bus entities, the naming, it's very much the same. A bus controller equals a network controller. A remote terminal is analogous to a network terminal, and an RT subaddress is analogous to an NT subaddress. FCAE 1553 is full duplex, so you can have basically multiple transactions or transfers occurring simultaneously. It's not a shared bus like 1553. So in addition to a higher bit speed on the network, you can also stack up and do exchanges of data in parallel with FCAE 1553. So, several fold increase in the throughput of data. Also, the address range is much larger on FCAE 1553. So where you can only have 31 RTs, you can have 16 meg RTs on an FCAE 1553 network. Also, a much larger number of sub-addresses at each RT, so up to 4 gig sub-addresses on FCAE 1553. The maximum size of messages that can be exchanged during the transfers is also much larger, so you can do up to 127 megabyte message transfers, where with 1553, it's 64 bytes is the maximum size of a message. And then also because it uses a switch topology, you're not limited by like the maximum length of the bus. So you can put switches along the way and basically by utilizing switches have a kind of an unlimited length of a bus or run of how far you can separate the nodes on an FCAE 1553 bus. If we look here at how a network terminal to network terminal exchange, fiber channel exchange would occur on an FCAE 1553 network. So at the network controller, you would start with a transmit command sequence. So you would have one or more frames indicating a transmit command, and that would be sent to the transmitting network terminal. Then that network terminal would start up in response to that a receive command to the receiving network terminal. That receive command would be carried in a receive sequence. That receive command would start an exchange initiated by the transmitting network terminal between the transmitting network terminal and the receive network terminal. And then over on the other side, when the initial transmit command is initiated, that would be an originating exchange that's initiated by the network controller. When the receiving network terminal has received all the data, the optional data sequences of the NT to NT exchange transfer, it would then send a status sequence back to the transmitting network terminal, which would trigger the transmitting network terminal to reply with a status to the originating network controller that initiated the NT to NT data transfer. So the picture here is showing you how you're on a network, you have multiple exchanges, fiber channel exchanges occurring at the same time, and multiple sequences within those exchanges occurring simultaneously to utilize the services and the functionality of fiber channel to execute what is very similar to a 1553 network terminal to network terminal or remote terminal to remote terminal data transfer. Next, we're going to talk about MIL Standard 1760. So MIL Standard 1760 is an aircraft store electrical interconnect standard. So it's a standard that defines the interfaces between an aircraft and the stores or weapons that would be attached to that aircraft. The MIL Standard 1760 interconnect standard defines the set of signals or the set of wiring and connections that are made between the aircraft and the store. MIL Standard 1760D utilized primarily for signaling MUX A and MUX B, which was a redundant MIL Standard 1553 bus. So MIL Standard 1760D is the MIL 1760 standard that preceded the availability or the release of high-speed 1760. In that standard, there were 4 high bandwidth signals that were primarily unused. They were left as for future growth in the original standard. When 1760E came along, those 2 of those 4 were utilized for HS1760 or high-speed 1760. So basically, they were used, used as an uplink and a downlink or a bidirectional link in a fiber channel link interface. They are a copper interface, so they are a 75 ohm copper interface, and so specifically high-speed 1760 does not use the fiber optic physical layer. It actually uses the 75 ohm coax physical, I think it's a single-ended interface that was already existing in the MIL Standard 1760 spec. So AS5653 is the protocol. It's a fiber channel protocol produced by SAE, the Society of Automotive Engineers, and it defines the network interface, or that high-speed network interface that is used on that fiber channel link that was added in MIL Standard 1760E. It's an upper layer protocol that defines the command and control messages. It utilizes or calls out and incorporates FCAE 1553 and also FCAV for video streaming over FCAE 1553. So whereas the legacy MIL Standard 1760 really only had the capacity to do 1553 type signaling transfers, with high-speed 1760 and MIL Standard 1760 there's an added capability to have video streams in the interface between the aircraft and the weapon, and that's realized by using FCAV protocol, which that defines how to encapsulate video on a fiber channel link. AS5653, as I said previously, it only allows for a switch fabric fiber channel topology, so there's no arbitrated loop and no point-to-point connections. AS5653 also calls out something called fast fabric initialization, or FFI. FFI was actually defined as an annex to one of the fiber channel standards, specifically FCSW4. That's one of the fiber channel switching standards. And that specifically defines what's called an avionics fabric, or an AE switch. And what's unique about an AE switch and its utilization of FFI is that it provides for accelerated and really fast initialization of the switch. We'll definitely talk about this more in one of the subsequent follow-on webinars, but at a high level, what's going on with FFI and NXD, there is, in an avionics environment, it contrasts to where like a traditional fiber channel, land-based lab, datacom type of application where you can have a very dynamically configured network. In avionics, you want the network to be very statically configured, and you also need it to basically be operational very quickly after a reset or at power on. And so that's primarily what fast fabric initialization provides. There's static configurations that are programmed into a master switch that's at the top of the switched fabric hierarchy. And at power up, that switch distributes the configuration, basically the routing tables, to all of the downstream switches, rather than relying on dynamic protocols to build switching and routing tables, which are more commonly used in non-avionics applications of fiber channel. Some product offerings that AIT has related to high-speed 1760. We offer a rugged AS5653 compliant switch and network controller. So it's a 4-port switch that also has an FCAE 1553 network controller built into it. We also provide a rugged XMC-based end node, an interface module that could go in a HS1760 node. That provides support for FCAE 1553, both network controller and network terminal operations, and it also includes support for streaming video using FCAV. We also provide an interface device that allows you to go from the standard SFP that you see in a lot of lab-based fiber channel interfaces, and that it will convert that from the normal, what's normally used as an optical SFP. In this case, it converts it to a 75 ohm coax bidirectional link that's compliant with 5653 75 ohm single-ended interface. So you can take that to convert a standard fiber channel interface that's typically communicating over an optical interface. Use this in that SFP socket on that fiber channel interface or device, and then it will convert that into the 75 ohm single-ended signal. We also provide and offer a full-up development and evaluation system if you happen to be new to HS1760 and are looking at evaluating it and doing some testing with the protocol. What this involves is 4 PCs, each have embedded in them a PCI Express interface device, basically what's equivalent to the XMC network controller and network terminal that's shown on the left there. embedded in each one of these PCs with driver software and sample applications so that each PC can act like a node on an FCAV 1553 network. And then also with that is delivered with that is our 16-port lab switch, which is FCAE compliant. It does the fast fabric initialization and operates like a compliant HS1760 network switch. So, summary of what we discussed today. Mil standard 1760D utilized previously, Mil standard 1760E utilizes what was previously unused 75 ohm coax signal lines in the Mil standard 1760D interface. On those coax signaling lines, AS5653 is used as the high-speed data bus. AS5653 is what's commonly known as or referred to as HS1760. And HS1760 utilizes FCAE 1553 or 1553 over Fibre Channel for control signaling, and it utilizes FCAV for streaming of video. It uses a copper physical interface, 75 ohm single-ended. HS1760 is also utilized on mini and micro munitions, which is a different standard than Mil standard 1760. And in those cases, it uses actually 150 ohm differential coaxial interconnect. And then at AIT, we provide a wide variety of 1760 products. We have, like I mentioned previously, the development and evaluation system. We have rugged and lab switches, FCAE lab switches. We also have rugged network controller and network terminal interfaces that also support streaming video with FCAV. We provide our protocol IP also for embedding on your own designs. And then we also have a full complement of test and simulation tools, which include both software and test instruments for testing high-speed 1760 networks. And as I mentioned at the start, keep an eye out for future invitations. This is the first webinar. With our next one, we intend to do a deeper dive into FCAE 1553A and AS5653. So talk a lot more about the protocol details and in more depth about how those are applied in weapons bus interfaces. That concludes today's webinar. I will hang out for a little bit. If you have any questions you want to send in through the chat, I'll try to reply to those. So I'll stay on for next 10-15 minutes here in case anybody wants to chat about anything. Also, feel free to reach out to us at AIT if you have further questions or looking for more information, and look forward to all of you joining the next webinar coming in the next several weeks. Thank you.